In this video, we're going to talk about closed loop control, which is a new way of controlling your motors. Previously, or rather up until now, we've been using percent output as our primary way of control. And in this video, we're going to be talking about controlling a motor to move at a specific velocity. So the first thing that we're going to do to sort of set ourselves up here is create a quote-unquote shooter subsystem, and all this really is just going to be one motor. And so what we're going to do is go ahead and make a new subsystem like usual. We'll call it shooter subsystem because usually the primary instance in which we control things with velocity is with the shooter. So I'm going to go ahead and do that, and then we're just going to declare one motor for now. So call it private shooter, WPI talent effects. We'll call the shooter motor equals new WPI. And for now, I'll just go ahead and assume it's ID 8. You can put in the ID that works best for you. And one thing that I actually wanted to show all of you is that there's actually an additional argument that you can pass into the WPI talent effects constructor. And that's the CAN bus that you are using. So one of the things that's really important to keep in mind in terms of wiring an FRC robot is something called your CAN utilization, which is essentially how many devices, or rather motors, are connected to a controller onto your robot. And by controller, I don't mean Xbox controller, I mean a controller like the Rio. And so you can actually wire your devices to different CAN buses. Now, what our team typically does is we wire a few to the RoboRio directly, so the RoboRio can have its own CAN bus. And then we also use a CTRE Canivore, which allows you to expand the number of CAN devices that you can connect to your robot, and that creates its own CAN loop as well. And so what you can do here is pass in the name of the CAN bus. So by default, this is set to Rio because we're assuming that all the motors are connected to Rio. But what you can actually do is pass in the name of your Canivore or other device that you have connected to this. So that's just something to point out. So you can leave this as Rio if you want. Or, of course, if you need to actually change it, you can go ahead and change it. But I just wanted to point that out. Okay, so we've got that. Now, what I want to do is set up the motor. Now this is going to be, we're going to add an extra step to this. So like usual, we're going to, shooter motor, we're going to config factory default. Now the next thing that we're going to need to do is tell the motor that we want to use its integrated sensor. So one of the nice parts about a Falcon is that it has an encoder built into it. And so that encoder gives us data on the motor's current position, which is going to be super valuable for a control mode, which again I'll detail later on in this video. So what we're going to do is shooter motor dot config selected feedback sensor, and it's going to be feedback device dot integrated sensor because we are using the built-in sensor. So now what we're saying is the motor is going to get all of its data from the integrated talent effects encoder inside the Falcon motor. So now that we've done all that setup, what I'd like to do now is talk about this new control mode. And to help us sort of visualize and understand, I've got this presentation here that we're going to take a look at. So the control mode that we're going to be talking about, or rather the foundation of it, is something called PID. So PID is essentially a way for you to reach a certain numerical goal. So let's get into that. So here's just a quick overview if you want to get that. But what it is it's essentially a feedback controller that tries to reach some numerical goal as fast as possible. And that numerical goal that you're reaching is what we call the set point, or rather the technical term for it. But basically, all it really is a way for you to get to a certain numerical value as fast as possible, given the physical constraints of your mechanism, obviously. So usually in the context of shooters, we're talking about RPM, revolutions per minute, and usually we want to reach a certain RPM value, and we want to be super specific with it. Now, the reason why PID is so important is because previously we worked with percent output. And the issue with percent output is that it's not super precise at reaching an exact numerical value at which you want to actuate your subsystems. So in the case of a shooter, there may be instances where running it at 50% might be incredibly varied in terms of what RPM your shooter is actually spinning at. So that's why we use PID, because we want to be able to run it at a speed that we set it to, not a speed that's contingent on hoping that percent output really works. So here we're talking about super precise control. That's the big difference here. So some other terms for PID, the error, which I'll be referencing, is just the difference between what the motor's current position or current velocity is and the set point or the target or the goal. And again, the goal of PID is to reduce the error and arrive at our set point. So if you want to picture a scenario in your head, let's say we want to spin our motor at 1000 RPM. Our motor is going to start at 0 RPM, right? So what we want to do with PID is figure out, given everything we know about our motor, or rather, given the way our motors actuate, what is the fastest way we can get to 1000 RPM? Because in some cases, you can't just immediately get there. So the way PID works is that we set 3 numerical constants. And so the first constant is called the proportional term. And so a technical definition for it is that it tries to make your positional error 0 by creating an output that is proportional to the error. And a more intuitive definition that I like to use is that it minimizes your error by making your output closer and closer to your set point. So the proportional term, you can think of it as like sort of doing the work to get you close to your set point as possible. And what the WPI lib docs have and what I really like is this analogy of a spring. So if you haven't taken physics, the way a spring works is that it has an equilibrium position where it's neither stretched or compressed. And what springs try to do is reach that equilibrium position. So if you imagine a spring in your hand and the direct middle is this equilibrium point, or sorry, let's say the far left is this equilibrium point. And when you stretch it out to the right, the force on the spring is going to act towards the left, right? Because the spring wants to go back to its equilibrium position. But now as it's going to the left, it's going to get compressed. And when it's compressed, it wants to go to the right to go back into equilibrium. So the force a spring experiences is proportional to its displacement from equilibrium, meaning the farther you stretch your spring, the more force it's going to experience. And similarly, the force applied by the controller, or the PID controller, is proportional to your error, meaning the greater your error is, the more quote-unquote force is going to be applied. And obviously, this is also dependent on your Kp constant, which we're going to talk about in a moment. The next term that I want to talk about is the derivative term in PID. So a technical definition is that it tries to drive the derivative of the error to 0 by outputting the controller proportional to the derivative of the error. A more intuitive definition that we like to use is that it dampens any potential overshooting caused by the proportional term. So sometimes so PID can actually be used by just a simple proportional loop. So you have this constant of proportionality, right? That's constantly multiplying your error, and you can easily reach your set point. But sometimes you might have a case of overshooting, or you want to get a little bit more precise with your control. This is where you can use a derivative term. And so overshooting over your set point can occur if your proportional constant is set too high. So using a derivative term can dampen the magnitude of each instance of overshooting. So it basically brings you closer to your goal in case you overshoot. And the last term is the integral term. And basically, a technical definition of it is it tries to drive the total accumulated error to 0 by controlling the output to be proportional to the sum of all the previous errors. And a more intuitive definition is it tries to drive your current position or error to your output. So it kind of acts as like the holding force if you're thinking about like something like an arm mechanism. And we usually don't really do integral terms when we do PID because there's something called integral windup. And basically what happens is if your I term is too high, then you might end up with something that overshoots forever. And integral terms are usually really, really, really small, but most PID loops that we use are totally fine with just P and D terms. We usually add I as a very last resort type thing. So here's just a visual of the position of a mechanism over time. I have some vocab terms here. They're not super important. The key part here is just understanding the visuals. So if you notice, the yellow curve is an oscillation. So those are underdamped, meaning what's going on here is that you're constantly overshooting your goal, then you're undershooting, and you're overshooting, you're undershooting. And if you notice, the magnitude, or rather the amplitude of this quote unquote, we'll call it a sine graph, or this sine curve or sinusoidal curve, is decreasing. So you eventually do reach your goal. It's just that you undergo a lot of oscillations in order to reach that goal. Now the green one's pretty cool, right? Like, because we're pretty much have this sort of exponential like curve, and we reach our goal, but not as quickly as the red one. And the red one is really where you want to have your PID constant set up, and ideally the situation in which you reach your set point. You want to be able to rise as fast as possible to somewhere close to your set point, and then you want to get to your set point, so you know that extra little oomph at the end, so that you actually arrive at your position, or in this case, what we're going to be talking about, your velocity. So again, just a quick recap. We're going to be controlling the motors to actuate at a specific velocity, and in order to do that, we need to use something called PID control. And the key here is setting your proportional, your derivative, and your integral terms. Those are going to be super important, and we will talk more about it. So the first thing that I want to do is set everything up in VS Code. So we already told the motor that we're using its integrated sensor, but the next thing that we need to do is set up our PID constants. So what you'll notice is that we have shooter motor config KP. And we can stick with this first constructor here for now. There's a slot ID argument that you'll notice here. Don't worry too much about this for now. Just leave that as 0. And I'm going to leave my value itself for 0 for now, because I'm going to talk about tuning these values after we set everything up. Then it's going to be shootermotor.config underscore ki, which again I'm going to leave to 0 for now. And then shootermotor.config kd, which again I will leave as 0. So now that we've set up our PID constants, we can now create a set method, and this time we'll call it set motor velocity. And this time we'll take in a double set point. I like to use STPT to abbreviate set point, and when we usually work with PID, it's nice to use set point, since that's a commonly known term instead of things like velocity or position. Just call it the set point. And the way it works is we do shooter motor.set, same thing as before. This time, the only difference rather is the control mode. It's going to be control mode.velocity, and then our set point. Now here's where things get interesting. So if we're working in the context of a shooter, that means that we're going to want to command this, or at least the units for velocity are going to be RPM, revolutions per minute. But Falcons do something interesting with their unit system, and if you'll notice, if I hover over this, the unit for velocity is position change per 100 milliseconds, or it's change in its tick values per 100 milliseconds, so change in the motor tick values per 100 milliseconds. And I don't know about you, but I don't really know what change in tick values per 100 milliseconds actually really means in terms of the motor and my spatial understanding. So what we can do is make a small helper class that allows us to do all these conversions. So what you can do is right-click this robot file, actually, and we're going to create a new file, and we'll call it unit conversion. And one thing to note is that if you're making a class separately without the WPILib helper, you have to specify that it's .java. So what I want to do is make a few methods that allows us to do some conversions. So let's make our first method is going to return a double, and it's going to be native units, meaning the Falcon's native units, to RPM, and we'll take in the native units. And I won't bore you with the math, so I'll just tell you what it is. It's going to be return native units times 600 divided by 2048. And then to go from RPM to native units, RPM, oops, well, static, load the C, up there, okay. It's just going to be return RPM divided by 600 times 2048, basically the reciprocal. Okay. So now that we've got these two methods, we should be good to go in terms of converting. So the set point that we pass into this method, we will assume that it is in RPM. So now what we can do is actually, let me get rid of this. We can say unit conversion dot, and we're going from RPM to native units because we are passing in an RPM and we want that to be converted to native units so that the Falcon can set it to its native units and for velocity. And the native unit, the RPM that we pass in is our set point. And there we go. That's pretty much it. So now what I want you guys to do is go ahead and write a command that calls the set motor velocity method. So go ahead and do that. And the set point that you can pass in is 1000. So take a second to do that. Okay, cool. So do is make a command. We'll call it run shooter command. Oops, sorry, we need to make a command. Now we can call it run shooter command. And we're just going to take in our subsystems. So this is going to be private shooter subsystem, and then that's all we should need. So it's going to be shooter subsystem S, shooter subsystem equals S, and then we're going to add requirements on the shooter subsystem, and then inside execute, we don't need to worry about any end conditions for now, but inside execute, it's going to be shooter subsystem.set motor velocity, and we're passing in 1000. Great, okay. Now what we can do is go ahead and quickly bind this to a button because I want to talk about being able to actually test this. So what I'll do is create a new joystick button, and I'll call this X button equals new joystick button, Xbox controller. I believe it's ABXY, so then this should be 3. Again, please feel free to check driver station for what this should be. Now what we can do is say, and let's make this while held. So xbutton.while true, new run shooter command. And we have to actually make the subsystem, or rather to initialize it. So private shooter subsystem equals new shooter subsystem. Cool. And now we can pass in shooter subsystem. And there we have it. Okay. So you're going to run this, and obviously it's not going to work because all of our PID values are 0. So it's not going to actually move. What we need to do now is figure out what PID values will make this work. And also one thing that I wanted to add before that is this unit conversion that we've done here will vary depending on your mechanism. This is just a pure conversion between RPM and native units, but depending on your mechanisms, you will have to multiply or divide by certain gear ratios, and especially for positional control, which you're going to have to multiply or divide by the gear ratio in order to get the actual revolutions of the motor. So you need to ask, or rather figure out what your gear ratios are and determine whether or not you need to be multiplying or dividing depending on if it's geared up or geared down. So that's another thing to keep in mind. For now, we're not going to worry about that. We're just going to stick with RPM to native units. Okay, so setting our P, I, and D values. So what I would recommend is start with a KP of 0.1 and don't set I and D. What's super helpful that I want to talk about now in terms of figuring out if your motor is actually running at the velocity it should be running at is using something called Smart Dashboard. So what we want to do is first write a method that gets our motor velocity. Because again, we're using the sensor on the Falcon, and the sensor on the Falcon can tell us what the current velocity of the motor is. And it's going to be in ticks per, or change in ticks per 100 milliseconds. So we're going to have to call unit conversion dot native units to RPM. And it's going to be shooter motor dot get selected sensor velocity. That's all. Now what we can do is use Smart Dashboard to print out these values. And Smart Dashboard, when printing out values, is very much like print line in Java. All it is we're going to call Smart Dashboard, and we're going to be putting a number. And now we can give a title to this number. In this case, let's call it shooter RPM. And get motor velocity. In order to fill that in for me. Cool. So what you can do now is open up Smart Dashboard. And when you deploy code on your robot, and so when you open Smart Dashboard, assuming you have a connection, and if you hit Control N, I'm not connected to a robot now, obviously, but what you can do, or what you should be able to see, is a box that shows shooter RPM. And that will allow you to numerically analyze what the shooter's RPM is as you hold down the X button on your controller. So right now we set P to 0.1, but if you notice any oscillations, or rather if it's overshooting, then you might want to cut down on your P. Or if it's not going high enough, increase your P. And if you see any oscillations, then maybe add a D turn. And that's sort of the intuition you should start to feel in terms of setting the shooter RPM. So it's important that you mess around with this a little bit and see what it's like in order to figure out what P, I, and D are individually responsible for. Because the only way you get the intuition for this is if you actually try it out yourself. So I can actually show you a cool way of visualizing the data on Smart Dashboard. And to do that, even though I'm not connected to a robot, what I can do is simulate robot code, which I was talking a little bit about before in one of our earlier videos. So WPILab has a way for you to simulate your robot code and actually trick the driver station into thinking that you're connected. And what I'm going to show you now is the code simulator running in the context of Smart Dashboard. And then later on in another video, I'll talk about the full utility of the code simulator. So it's probably going to build my code, which might take a second. And all I did was hit the command palette and hit simulate. So I'm going to give this a second to compile. And then what you want to do is simulate and use a real driver station. So you'll notice this window pop up. We're not going to talk about this just yet. But what I can do is go ahead and open driver station. And you'll notice that we have the green light for communications and robot code, which is very cool. And it's going to open shuffleboard as well because that's the way I have it set up. I'm going to close that. Okay. Now if I open, not this, Smart Dashboard, you'll notice I've got a window for shooter RPM, which is cool. Now obviously it's going to be 0 because I don't have a controller plugged in and I'm not enabled. But what you can do is if you go to View and click Editable, you can now move this around, which is nice. But another cool thing you can do is if you right-click it, you can change to a line plot. And now you can get a graph. And what you want to do is make sure this graph looks exactly like, or as close as you can, to the curve that I showed you on the presentation. So now you have a cool way of visualizing the set points that your shooter RPM is arriving at when you actually run this. So what I would recommend is set it to 0.1, run the shooter by holding on the button on the controller, and then notice the behavior. So you want to hold it, and you want to hold it for a long time and see how long it takes for it to arrive at its target RPM. And what you want to do is figure out, how do I make that as fast as possible? Is it adding more P? Is it reducing P? Is it adding a D? I would not worry, is it adding a D term, or is it decreasing the D term, whatever it may be. I would not worry just yet about adding an integral term unless you see it's absolutely necessary. But try to do it with just P and D. You should 100% be able to. So once you've got that done, you should be good to go. And that wraps up this video, and we'll catch you in the next one.